The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
I'm Haynes Miller. I'm substituting for David Jarrison today. So you have a substitute teacher today. So I haven't been here in this class with you, so I'm not completely sure where you are. I think you've just been talking about differentiation, and you've got some examples of differentiation, like these basic examples. The derivative of x to the n is in x to the n minus 1. And I think maybe you spent some time computing the derivative of the sine function as well recently. And I think you have some rules for extending these calculations as well. For instance, I think you know that if you differentiate a constant times a function, what do you get? The constant comes outside like this. Or I could write Cu prime is Cu prime. That's this rule, multiplying by a constant. And I think you also know about differentiating a sum. Or I could write this as u plus v prime is u prime plus v prime. So I'm going to be using those, but today I'll talk about a collection of other rules about how to deal with a product of functions, a quotient of functions, and best of all, composition of functions. And then at the end, I'll have something to say about higher derivatives. So that's the story for today. That's the program. So let's begin by talking about the product rule. So the product rule tells you how to differentiate a product of functions, and I'll just give you the rule. First of all, the rule is it's u prime v plus u v prime. A little bit funny, differentiating a product gives you a sum. But let's see how that works out in a particular example. For example, suppose that I wanted to differentiate the product. Well, the product of these two basic examples that we just talked about, I'm going to use the same variable in both cases instead of different ones like I did here. So the derivative of x to the n times sine of x. So this is a new thing. Couldn't do this without using the product rule. So the first function is x to the n, and the second one is sine of x, and we're going to apply this rule. So u is x to the n, u prime is, according to the rule, n x to the n minus 1. And then I take v and write it down the way it is, sine of x. And then I do it the other way. I take u the way it is, that's x to the n, and multiply it by the derivative of v, v prime. We just saw v prime is cosine of x. So that's it. Obviously, you can differentiate longer products of more things, by doing it one at a time. Well, let's see why this is true. I want to try to show you why the product rule holds. So I think you have a standard way of trying to understand this. And it involves looking at the change in the function that you're interested in differentiating. So I should look at how much the product uv changes when x changes a little bit. Well, so how do we compute the change? Well, I write down the value of the function at some new value of x plus delta x. Well, I better write down the whole new value of the function, and the function is u times v. So the whole new value looks like this. It's u of x plus delta x times v of x plus delta x. That's the new value. But what's the change in the product? Well, I'd better subtract off what the old value was, which is u of x times v of x. OK. Now, according to the rule we're trying to prove, I have to get u prime involved. So I want to involve the change in u alone by itself. Let's just try that. I see part of the formula for the change in u right there. Let's see if we can get the rest of it in place. So the change in x is u of x plus delta x minus u of x, right? That's the change in x. It occurs, this part of it occurs up here multiplied by v of x plus delta x. So let's put that in too. Now this equality sign isn't very good right now. I've got this product here so far, but I've introduced something I don't like. I've introduced u times v of x plus delta x, right? Minus that. So the next thing I'm going to do is correct that little defect by adding in u of x times v of x plus delta x. Okay, now I've canceled off what was wrong with this line, but I'm still not quite there because I haven't put this in yet. So I'd better subtract off u of x, u times v, and then I'll be home. But I'm going to do that in a clever way because I notice that I already have a u here. So I'm going to take this factor of u and make it the same as this factor. And so I get u of x times this minus u of x times that. That's the same thing as u times the difference. So that was a little bit strange, but when you stand back and look at it, you can see, multiply it out, the middle terms cancel, and you get the right answer. Well, I like that because it's involved the change in u and the change in v. So this is equal to delta u times v of x plus delta x minus u of x times the change in v. Well, I'm almost there. The next step in computing the derivative, take the difference quotient, divide this by delta x. So delta of uv divided by delta x is, well, I'll say delta u divided by delta x times v of x plus delta x. Have I made a mistake here? This plus magically became a minus on the way down here, so I'd better fix that. Plus u times delta v over delta x. This u is this u over here. So I've just divided this formula by delta x, and now I can take the limit as x goes to 0. So this, as delta x goes to 0, this becomes the definition of the derivative. And on this side, I get du dx times, now, what happens to this quantity when delta x goes to 0? So I'm getting closer and closer, so this quantity is getting closer and closer to x, so what happens to the value of v? It becomes equal to x of v. That uses continuity of v. So v of x plus delta x goes to v of x by continuity. So this gives me times v, and then I have u times, and delta v delta x gives me dv dx. And that's the formula. That's the formula as I wrote it down at the beginning over here. The derivative of a product is given by this sum. Yeah?
How did we get from the first line to the second of the long equation?
From here to here? Well, So maybe it's easiest to work backwards and verify that what I wrote down is correct here. So if you look, there's a u times v of x plus delta x there, and there's also one here. And they occur with opposite signs. So they cancel, and what's left is u of x plus delta x times v of x plus delta x minus u times v, and that's just what I started with.
But wouldn't the addition and subtraction, I mean, they cancel, right?
I canceled out this term, and what's left is the ends. Any other questions, though? Yes? Well, I just calculated what delta uv is, and now I'm going to divide that by delta x on my way to computing the derivative. And so I copied down the right-hand side and divided by delta x. I just decided to divide the delta u by delta x and the delta v by delta x. Good. Anything else? So, all right, so we have the product rule here, the rule for differentiating a product of two functions. This is making us stronger. There are many more functions you can find derivatives of now. How about quotients? Let's find how to differentiate a quotient of two functions. Well, again, I'll write down what the answer is, and then we'll try to verify it. So there's a quotient. Let me write this down. There's a quotient of two functions. And here's the rule for it, so I always have to think about this and hope that I get it right. U prime v minus uv prime divided by v squared. This may be the craziest rule you'll see in this course, but there it is. And I'll try to show you why it's true and see an example. Yeah, there was a hand. Sorry? What letters look the same? U and V look the same? I'll try to make them look more different. The V's have points on the bottom. The U's have little round things on the bottom. What's the new value of U? The value of U, the value of U at x plus delta x, it's U plus delta U, right? That's what delta U is. It's the change in U when x gets replaced by delta x. And the change in V, the new value of V is V plus delta V. So this is the new value of U divided by the new value of V. That's the beginning. And then I subtract off the old values, which are U minus V. This will be easier to work this out when I write it out this way. So now I will cross multiply, as I said. So I get UV plus delta U times V minus, now I'll cross multiply this way, you get UV minus U times delta V. And I divide all this by V plus delta V times U. Okay. Now the reason I like to do it this way is that you see the cancellation happening here. UV and UV occur twice, and so I can cancel them. And I will. And I'll answer these questions in a minute. Ooh, that's a V. All right. Good. Anything else? That's what all the hands were. Good. All right, so I cancel these, and what I'm left with then is delta U times V minus U times delta V, and all this is over V plus delta V times V. Okay, there's the difference. There's the change in the quotient. The change in this function is given by this formula. And now, to compute the derivative, I want to divide by delta x and take the limit. So let's write that down. Delta of uv divided by delta x is this formula here divided by delta x. And again, I'm going to put the delta x under these delta u and delta v, okay? I'm going to put delta x in the denominator, but I can think of that as dividing into this factor and this factor. So this is delta u over delta x times v minus u times delta v over delta x, and all that is divided by the same denominator, v plus delta v times v. Right? Put the delta x up in the numerator there. Next up, take the limit as delta x goes to 0. I get, by definition, the derivative of u divided by v. And on the right-hand side, well, this is the derivative du dx, right? Times v, and then u times, and here it's the derivative dv dx. Now, what about the denominator? So when delta x goes to 0, v stays the same, v stays the same. What happens to this delta v? It goes to 0 again because v is continuous. So again, delta v goes to 0 with delta x because they're continuous, and you just get v times v. I think that's the formula I wrote down over there. The derivative of u times v minus u times the derivative of v, and all divided by the square of the old denominator. Well, that's it. That's the quotient rule. Weird formula. Let's see an application. Let's see an example. So the example I'm going to give is pretty simple. I'm going to take the numerator to be just 1. So I'm going to take u equals 1. So now I'm differentiating 1 over v. The reciprocal of a function, 1 over a function. Here's a copy of my rule. What's du dx in that case? U is a constant, so that term is 0 in this rule. I don't have to worry about this. I get a minus, and then u is 1, and dv dx, well, v is whatever v is. I'll write dv dx as v prime. And then I get a v squared in the denominator. So that's the rule. Minus, I could write it as v to the minus 2 v prime. Minus v prime divided by v squared. That's the derivative of 1 over v. How about an even a sub-example of that? I'm going to take the special case where u is equal to 1 again, and v is a power of x. And I'm going to use the rule that we developed earlier about the derivative of x to the n. So what do I get here? D over dx of 1 over x to the n is, I'm plugging into this formula here, with v equals x to the n. So I get minus v to the minus 2. All right, if v is x to the n, v to the minus 2 is, by the rule of exponents, x to the minus 2n. And then v prime is the derivative of x to the n, which is n x to the n minus 1. Okay, so let's put these together. There's several powers of x here. I can put them together. I get n times x to the minus 2n plus n minus 1. One of these n's cancels, and what I'm left with is minus n minus 1. So we've computed the derivative of 1 over x to the n, which I could also write as x to the minus n, right? So I've computed the derivative of negative powers of x, and this is the formula that I get. If you think of this minus n as a unit, as a thing to itself. It occurs here in the exponent, it occurs here, and it occurs here. So how does that compare with the formula that we had up here? The derivative of a power of x is that power times x to 1 less than that power. That's exactly the same as the rule that I wrote down here. But the power here happens to be a negative number, and the same negative number shows up as a coefficient, and there in the exponent. Yeah? How did I do this? Sorry? Right. Where did that x to the minus 2n come from? So the rule, I'm applying this rule. So the denominator in the quotient rule is v squared. And v was x to the n. So the denominator is x to the 2n. And I decided to write it as x to the minus 2n. So the green comments there, what they say is that I can enlarge this rule. This exact same rule is true for negative values of n as well as positive values of n. So there's something new in your list of rules that you can apply, of values of the derivative. That standard rule is true for negative as well as positive exponents. And that comes out of the quotient rule. Okay, so we've done two rules. I've talked about the product rule and the quotient rule. What's next? Let's do the chain rule. So this is a composition rule. So the kind of thing that I have in mind, composition of functions is about substitution. So the kind of function that I have in mind is, for instance, y is the sine of t raised to the 10th power. That's a new one. Haven't seen how to differentiate that before, I think. This kind of power of a trig function happens very often. You've seen them happen as well, I'm sure already. And there's a little notational switch that people use. They'll write sine to the 10 of t. But remember that when you write sine to the 10 of t, what you mean is take the sine of t and then take the 10th power of that. That's the meaning of sine to the 10 of t. So the method of dealing with this kind of composition of functions is to use new variable names. What I mean is, I can think of this sine of t raised to the 10th power, I can think of it as a two-step process. First of all, I compute the sine of t, and let's call the result x. There's the new variable name. And then I express y in terms of x. So y says take this and raise it to the 10th power. In other words, y is the function x to the 10th power. And then you plug x equals sine of t into that, and you get the formula for what y is in terms of t. So it's good practice to introduce new letters when they're convenient, and this is one place where it's very convenient. So let's find a rule for differentiating a composition, a function that can be expressed by doing one function and then applying another function. And here's the rule. Well, maybe I'll actually derive this rule first, and then you'll see what it is. In fact, the rule is very simple to derive. So this is a proof first, and then we'll write down the rule. I'm interested in delta y over delta t. y is a function of x is a function of t, and I'm interested in how y changes with respect to t, with respect to the original variable t. Well, because of that intermediate variable, I can write this as delta y divided by delta x times delta x divided by delta t. It cancels, right? The delta x cancels. The change in that intermediate variable cancels out. This is just basic algebra. But what happens when I let delta t get small? Well, this gives me dy dt. And on the right-hand side, I get dy dx times dx dt. So students will often remember this rule, this is the rule, by saying that you can cancel out the dx's. And that's not so far from the truth. That's a good way to think of it. In other words, this is the so-called chain rule. And it says that differentiation takes of a composition is a product. It's just the product of the two derivatives. So that's how you differentiate a composite of two functions. And let's just do an example. Let's do this example. See how that comes out. So let's differentiate. What did I say? Sine of t raised to the 10th power. Okay, there's an inside function and an outside function. The inside function is x as a function of t. That is, this is the inside function. And this is the outside function. So the rule says, first of all, let's differentiate the outside function. Take dy dx. Differentiate it with respect to that variable x. The outside function is the 10th power. What's its derivative? So I get 10x to the 9th power. I'm using in this account, I'm using this newly introduced variable name x. So the derivative of the outside function is 10x to the 9th, and then here's the inside function, and the next thing I want to do is differentiate it. So what's dx dt? d sine t, the derivative of sine t, all right, that's cosine t. That's what the chain rule gives you. This is correct, but since we were the ones to introduce this notation x here, that wasn't given to us in the original problem here. The last step in this process should be to substitute back in what x is in terms of t. So x was sine of t, so that tells me that I get I get 10 times sine of t raised to the 9th power, that's x to the 9th, times the cosine of t, or what's the same thing, sine to the 9th of t, cosine of t. So there's an application of the chain rule. You know, people often wonder where the name chain rule comes from. I was just wondering about that myself. Is it because it chains you down? Here's a chain. Is it because it chains you down? Is it like a chain fence? I think I've decided what it is. It's because by using it, you burst the chains of differentiation, and you can differentiate many more functions using it. So when you want to think of the chain rule, just think of that chain there. It lets you burst free. Let me give you another application of the chain rule. Ready for this one? So I'd like to differentiate the sine of 10t. Now, okay, so this is again, it's a composite of two functions. What's the inside function? Okay, so I think I'll introduce this new notation. X is 10t, and the outside function is the sine. So y is the sine of x. So now the chain rule says dy dt is, okay, let's see. I take the derivative of the outside function, and what's that? Sine prime. We can substitute what we know what sine prime is. So I get cosine of whatever, x, and then times what? Now I differentiate the inside function, which is just 10. So I could write this as 10 cosine of what? 10t. X is 10t. Now, once you get used to this middle variable, you don't have to give a name for it. You can just think about it in your mind without actually writing it down. d of sine of 10t, I'll just do it again without introducing this middle variable explicitly. Think about it. I first of all differentiate the outside function, and I get cosine, but I don't change the thing that I'm plugging into it. It's still x that I'm plugging into it. X is 10t. So let's just write 10t and not worry about the name of that extra variable. If it confuses you, introduce the new variable and do it carefully and slowly like this. But quite quickly, I think you'll get to be able to keep that step in your mind. I'm not quite done yet. I haven't differentiated the inside function. The derivative of 10t is 10. So you get, again, the same result. A little shortcut that you'll get used to. Really and truly, once you have the chain rule, the world is yours to conquer. It puts you in a very, very powerful position. Okay, well, let's see. What have I covered today? I've talked about product rule, quotient rule, composition. I should tell you something about higher derivatives as well. So let's do that. This is a simple story. Higher is a kind of a strange word. It just means differentiate over and over again. All right, so let's see. If we have a function u, or u of x, please allow me to just write it as briefly as u. Well, I can, this is a sort of notational thing. I can differentiate it. I get u prime. That's the derivative. That's a new function. Like if you started with the sine, that's going to be the cosine. A new function, so I can differentiate it again. And the notation for the differentiating it again is u prime prime. So u prime prime is just u prime differentiated again. For example, if u is the sine of x, so u prime is the cosine of x. Has Professor Jerrison talked about what the derivative of cosine is? What is it? Ha! Okay, so u prime prime is minus the sine of x. Let me go on. What do you suppose u prime prime means? I guess it's the derivative of u prime prime. It's called the third derivative. And u prime prime is called the second derivative. And it's u prime prime differentiated again. So to compute u prime 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 in this example, what do? I differentiate that again. There's a constant term, minus 1, constant factor. That comes out. The derivative of sine is what? Okay, so the u prime prime is minus the cosine of x. Let's do it again. Now, after a while, you get tired of writing these things, and so maybe I'll use the notation u upper 4. That's the fourth derivative. That's u prime 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 prime, or it's u prime 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 differentiated again, fourth derivative. And what is that in this example? Okay, the cosine has derivative minus the sine, like you told me, and that minus sign cancels with that sign, and altogether I get plus the sine of x. That's pretty bizarre. When I differentiate the function sine of x 4 times, I get back to the sine of x again. That's the way it is. Now, this notation, prime, 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 and things like that, there are different ways of, there are different variants of that notation. Other notation, for example. As another notation, well, you've used the notation du dx before. U prime also could be denoted du dx. I think we've already here today used this way of rewriting du dx. I think when I was talking about d dt of uv and so on, I pulled that d divided by dt outside and put whatever function you're differentiating over to the right. So that's just a notational switch. It looks good. It looks like good algebra, doesn't it? As a further, but what it's doing is regarding this notation as an operator. It's something that you apply to a function to get a new function. I apply it to the sine function and I get the cosine function. I apply it to x squared and I get 2x. This thing here, that symbol, represents an operator which you apply to be applied to a function. And the operator says, take the function and differentiate it. So a further notation that people often use is they give a different name to that operator and they'll write capital D for it. So this is just using capital D for the symbol d dx. So in terms of that notation, let's see. Let's write down what higher derivatives look like. So let's see. That's what u prime is. How about u prime prime? Let's write that in terms of the d dx notation. Well, I'm supposed to differentiate u prime, right? So that's d dx applied to the function du dx. Differentiate the derivative. That's what I've done. Or I could write that as d dx applied to d dx applied to u, just pulling that u outside. So I'm doing d dx twice. I'm doing that operator twice. I could write that as d dx quantity squared applied to u. Differentiate twice and do it to the function u. Or I could write it as, now this is a strange one. I could also write, this I guess says like that. It's getting stranger and stranger, isn't it? This is definitely just a kind of abusive notation, but, and then And then people will go even further and write d squared u divided by dx squared. So this is the strangest one. This equality is the strangest one because you may think that you're taking d of the quantity x squared, but that's not what's intended. This is not d of x squared. What's intended is the quantity dx squared. In this notation, which is very common, what's intended by the denominator is the quantity dx squared. It's part of this second differentiation operator. So I've written a bunch of equalities down here, and the only content to them is that these are all different notations for the same thing. You'll see this notation very commonly. And so, for instance, the third derivative is d cubed u divided by dx cubed, and so on. Sorry?
Distance for part B.
Ooh, someone's talking. Yes, absolutely. Or an equally good notation is to write the operator capital D done 3 times to u. Absolutely. So I guess I should also write over here when I was talking about d squared, the second derivative, another notation is do the operator capital D twice. Let's see an example of how this can be applied. I'll answer this question. Yeah, so the question is whether the fourth derivative always gives you the original function back, like what happened here. No, that's very, very special to sines and cosines, right? And in fact, let's see an example of that. I'll do a calculation. Let's calculate the nth derivative of x to the n. Okay, n is a number like 1, 2, 3, 4. So here we go. Let's do this. So let's do this bit by bit. What's the first derivative of x to the n? So everybody knows this. I'm just using a new notation, this capital D notation. So it's n x to the n minus 1. And now you know, by the way, n could be a negative number for that. But for now, for this application, I want to take n to be 1, 2, 3, and so on. One of those numbers. OK, we did one derivative. Let's compute the second derivative of x to the n. Well, there's this n constant that comes out, and then the exponent comes down, and it gets reduced by 1. Right? Shall I do one more? D cubed x to the n is n times n minus 1. That's the constant from here, times that exponent, n minus 2, times 1 less n minus 3. It's the new exponent. Well, I keep on going until I come to a different blackboard. Now, I think I'm going to stop when I get to the n minus first derivative so we can see what's likely to happen. So when I took the third derivative, I had the n minus third power of x. And when I took the second derivative, I had the second power of x. So I think what will happen when I have the n minus first derivative is I'll have the first power of x left over. The powers of x keep coming down. And when I've done it n minus 1 times, I get the first power. And then I get a big constant out in front here, times more and more and more of these smaller and smaller integers that come down. What's the last integer that came down before when I got x to the first here? Well, let's see. It's just 2, because this x to the first power occurred as the derivative of x squared, and the coefficient of that is in front of that is 2. So that's what you get. The numbers n, n minus 1, and so on down to 2 times x to the first. And now we can differentiate one more time and calculate what, this is x to the n, and calculate what dn x to the n is. So I get the same number, n times n minus 1, and so on, times 2. And then I guess I'll say times 1, times, what's the derivative of x to the 1? 1. So times 1, if you like, times 1 times 1, where this 1 means the constant function 1. Does anyone know what this number is called? That has a name. It's called n factorial. And it's written in exclamation point. And we've just used an example of mathematical induction. So the end result is dn x to the n is n factorial constant. Okay, that's a neat fact. Final question for the lecture is, what's d to the n plus 1 applied to x to the n? Ha, excellent. It's the derivative of a constant, so it's 0. Okay, thank you.